I'll record this and post it online, and you can look at it, so you're welcome to take notes if you like. Otherwise, you can just kind of kick back and pay attention and ask questions and then look at it later. Okay, so this is my little spiel on how to factor polynomials. Factor polynomials. Okay, so there's going to be 5 techniques that we're going to talk about, and then we're going to follow those techniques one by one to factor, hopefully, any polynomial. They begin with like the easiest thing you could do. So number 1 is going to be to factor a monomial. Factor a monomial. What does that mean? Okay, so we're going to look at our polynomial and we're going to determine if there is a common factor to all the terms that can be factored out and simplified in an easy manner. So for example, let's say we had something like 9x squared y to the 4th power plus 18x y to the 5th power minus 27x to the 3rd power y squared. Okay, and we had that ugly, nasty thing, and they told us to factor that. All right, well, the first place you should start is noticing that they all have some common factors. This has a 9, that's a factor of 9, that's a factor of 9. They all have some x's, they all have some y's. So we want to figure out what is the biggest common factor to all of them. So the 9 is there. I can put a 9 out there. And x, they all have at least one x. They don't have 2 x's in common because this one only has 1. Right? So I want something common to all of them. And then the most that they all have in common is, for the y's, is the y squared. So I can factor that out. All right, so now I'm going to rewrite this as this times something like this, where this times this is this times the middle one is the middle one, and this times the last one is that. So it's kind of like the reverse of distribution. So blank times 9 is 9, well, that's just going to be 1. And then x times blank is x squared, that's supposed to be an extra x, y squared. And then blank times 9 is 18, that's going to be a 2 in there. Then no x is required, and then y to the power of 3. So this times this equals that. Minus, and then 9 times 3 equals 27, and then the x squared value there, and then we don't need a y. Got it. Okay, so that's the first thing we want to do. Factor a monomial, check your polynomial to see if something is common to all 3 or 4 or however many terms you have. Something common to all of them that we can pull out and factor it as much as possible. That often simplifies life. Okay, that's the first one. The second one now is factor by grouping. Now, factor by grouping is kind of a result of the following thing. So kind of a side thing here. Recall that the way we multiply binomials, like let's say we had this one plus y times x plus b. Let's say I had to multiply that. Multiply. Okay, so in America, right, we do it our way. And our special way would be to FOIL this thing, right? Americans love to FOIL. Really? Really? Oh, whatever. You get the point. We're going to end up with x squared plus this times this gets you xb, plus this times this gets you xy, plus this times this gets you plus by. And then nothing else combines, so we're happy that way, right? Okay, that's one way to multiply. Another way, a big or here, same thing, is the following idea. How would we multiply w times x plus b? Well, we distribute, right? So this would be equal to wx plus wb. Right? Okay. Well, what if it wasn't just a w? What if it was a binomial like that one? X plus y times x plus b. Well, we could FOIL, or what we could do is distribute this entire thing, this over there, thus giving me x plus y times x plus, and then x plus y times b. Good? Questions? Yeah, sort of. Right, so here it was the w that got distributed, w times x, w times b. But here it's this entire thing of x plus y times x plus y times b. And that's how we get this. And then we do one more round of distributing going that way, and we end up with x squared plus yx plus xb plus yb. So we get the exact same answer as that one. Maybe some things are flipped around a little bit, but really you get the same answer as that one. Okay, why do we care about that? But because what we're going to do in this next factoring technique is to follow this process in reverse. We're going to be given something that looks like this, and what we're going to do is use our little algebra skills to rewrite it like that, and then this is the hard step. We're going to notice that this is really one little unit here, the x plus y. This is the same little unit, x plus y. So we have this little binomial where this is one term and this is another term. This is the addition. And then we're going to notice that this and this are common, and we're going to factor it out and pull it out there. So it's this step in reverse that's going to be kind of tricky. But that's what factored by grouping is. Okay, so we're going to start there. We're going to focus on factoring the first two to get that. Then we're going to work on getting this over here. We're going to notice that these two are identical and factor it. All right, let's look at an example. How about this one? So technique number 2 is factor by grouping. And in fact, let me write down the instructions. They might not make too much sense right now, but then we'll see an example and we'll follow step by step on the instructions so I see what I mean by that. Step number 1 for factor by grouping is factor the first two terms. Factor the first two terms. Step number 2, we're going to add the plus symbol. Add the plus sign. Then step number 3, insert a blank space. Blank space. Step number 4, copy the binomial from step 1. And step number 5, factor the common binomial. Oh, no, sorry, fill in the blank. Fill in the blank to make a true statement with the original equation. Again, when we do an example, you'll know what that means. And then finally, factor the common binomial. Factor the common binomial. Okay, so let's go through each one of these and see what we are supposed to do. So let's say we are given this one. How about this? Factor, and we got ourselves 2x to the fourth y. 2x to the fourth y plus 24x to the third y squared plus 70x squared y. Oh, damn, I don't want that one. Why did I copy that one? Sorry, I want 4x to the third power minus x squared minus 16x plus 4. Okay, so there it is. The first thing we do is think about rule number 1. Is there a common factor to all the terms? And in this case, there isn't, right? These have x's, but that one doesn't have any x. And then these have a 4, but this one has a 4, but that one doesn't have a 4. So there are no numbers or letters common to all the terms. I cannot do anything with the first factoring technique. I'm on to number 2. Number 2, I'm going to focus on the first two terms. What do they have in common? They have a x squared in common, right? Okay, so I'm going to focus on the first two that have an x squared in common, and then I factor that out, I'll get a 4x minus 1. That's the first step. Factor the first two terms. Ignore the last two. Just the first two, factor them out. Okay, next step, add a plus sign. Always a plus sign. Next step, add a blank. Plus blank. Okay? Next step, copy the binomial you just created in step 1. That's this guy. Copy the binomial. 4x minus 1. Okay? So factor the first two terms, put a plus sign, put a blank, copy the binomial. Next step, fill in that blank. So you want to fill in this blank to make a true statement with the original polynomial. So we want this to be equal to the original polynomial. So blank times 4x equals to negative 16x. Be careful about the signs. So what goes in that blank?
Negative 4.
Minus 4. Negative 4 times 4x gives you negative 16. Negative 4 times minus 1 gives you positive 4. Okay, so that's this guy. Fill in the blank to make a true statement with the original equation. And finally, the tricky part, noticing that this is a common binomial that can be factored out. So this would be 4x minus 1, parentheses, x squared minus 4. Good? All right, so this guy comes from there, and this guy comes from there. And so we're saying that this times this equals this, and this times that equals that out there. Okay, and that's the end of factor by grouping. Now this particular one you can continue, and that leads into the next factoring technique. But for now, that is the factor by grouping process. So let me pause for a second here. What do you think? Any questions, ideas, concerns?
This is isn't this like similar? Oh wait, we use this in the AC method, right?
We're building to that. AC method is our fifth factoring technique. It's not the same. How are they different? Well, one very easy way to spot this is that I need a minimum of 4 terms because I want the first 2 to go here and then I want the last 2 to go there. So I need an even number of terms that's equal to 4 or more. So right over here, I'm going to put in parentheses, we need 4 terms, 4 or 6 or 8 or 12 or 10 or 12 terms. Okay? But I mean, come on, no one's going to give you a 6-term polynomial of factor. We're not that cruel. So really that's all you have to focus on, 4 terms. I think once in my life I saw a book give a 6-term polynomial of factor. It was an awesome book. But I don't think any of our questions have that in this book. So 4 terms. That's a key to being able to tell that this is a factor by grouping question. You see 4 terms, factor by grouping. Try it out. It might not work. It's not guaranteed that it's going to work just because you have 4 terms, but it's something worth trying. And no, the AC method doesn't apply when you have 4 terms like that. The AC method applies for something else. We'll get to it in a little bit. Okay, but we're okay with this one?
Yeah.
You see 4 terms, do this process, and that should lead to it. Okay, so now we're going to go down to our third factoring technique. Our third factoring technique is to notice some patterns. Right? There's really no math in that one. This one's just pattern recognition. Okay, so the third thing we want to do is factor by pattern recognition. Okay, so what are the patterns that we've run into in the past? Well, let me refresh your memory of the popular ones. If we had something like a plus b squared, we know that that's a from multiplication, that's a plus b times a plus b. And then when we FOIL that all out, we get a squared plus ab plus another copy of ab plus a b squared. And then the middle 2 combine to give you this. Right? Okay, so when we multiply, we were going this way. But now we're going to be given this, and we want to be able to recognize that this is the pattern they gave me and go backwards and go to this guy. Right? So now we want to go backwards, and that's called factor. Factor. Go that way. Okay? So for example, let me give you some numbers in here. How about if we had something like x plus 7 squared? All right, well, we know that that's going to be x plus 7 times x plus 7. FOIL that whole thing out, we get x squared plus 7x plus another 7x plus a 49, which is equal to x squared plus 14x plus 49. Okay, so now, if this is given, so now, factor x squared plus 14x plus 49, well, all you have to do is go, hey, wait a minute, this fits this pattern. This is equal to something squared, and then this is equal to something squared at the end, and then in the middle it's equal to twice the 2 things that you're squaring. This is exactly the same thing as that. This fits this pattern. Something squared in the beginning, something squared at the end, the middle part is twice the two things that you're squaring. It fits this pattern, so all you'd have to do at this point is, since you've recognized it, is just to say that this is equal to that. So that's the really one, that's the one I think that it confuses a lot of people, because people that have practiced this a lot, and trust me, they're not smart or anything, they just practice this a lot, they just recognize these really quickly and they jump to it, right? And then other people that haven't, they think they're just geniuses, right? They just look at that and they go, oh, the answer is x plus 7 squared. And you're like, oh, how did they figure that out? Well, it's just this little pattern. Okay, so you have to know these patterns. Let's look at another pattern. There's only a few patterns that we deal with. So there's this one here, and then there is the one with a minus. How about if we had a minus b squared? Well, that's just going to be a minus b times a minus b. If we FOIL it, we get a squared minus a b minus another a b plus b squared, right? Because we have a negative times a negative, giving you a plus b squared. And the middle terms are going to be a squared minus 2ab plus b squared. So that's the other pattern that we're going to work with. In fact, let me start writing them over here so we can see them and we can write them down. So I'm going to write them in this direction because this is what we're going to be starting with, and we want to factor it in the other direction. So pattern number 1 is this: a squared plus 2ab plus b squared. If you see something like that, then this factors as a plus b squared. Good. People don't like a and b as much. How about if I write it with like x and x squared plus 2xy? No, I don't like y. How about, let's stick to a. 2xa plus a squared. Same thing, right? They're just letters. It doesn't matter what the letter is. We're saying one thing squared there, another thing squared there, and the middle is twice the two things that you're squaring. That's one pattern. And so this guy will factor as x plus a squared. Okay, and then over there we just found another one. This one says that if we have x squared minus 2xa plus, what did I do? Yeah, 2xa plus a squared out there, that this guy factors as x minus a squared. Because it's this pattern right here. So if I see this pattern, I know it's that. Just a couple more patterns that are popular. One of them is this. If we had a plus b times a minus b, conjugates, they're identical in every way, shape, and form except one has a plus, one has a minus. Then when we FOIL them, what do we get? A squared minus ab plus ab minus b squared. And then the middle terms cancel out. We just get this. We call that a difference of squares. And so again, we are going to start with that, and we're going to go, hey, I know that pattern, it equals that. So we're going to go over here, I'm going to write that one down. A squared minus b squared is equal to a plus b times a minus b, like that. Right, and again, the letters, doesn't matter what letter you use, but I guess just to stay consistent, I'm going to rewrite it again and just put a's and x's here. So if I have x squared minus a squared, then that's going to be x plus a times x minus a. Okay. I like to put this pattern down just to point out to people, if we have a subtraction there, a difference of squares, that's what this one's called, difference of squares, this guy. But if we have a plus there, does not factor. So let's just write it in there, just to remind people that that one doesn't. It's important to have the subtraction in there. If we have an addition, you're done. It doesn't factor anymore. You're done. Okay. These two are called perfect square trinomials. Square trinomials. You know, these are very popular, so they have extra little names. And then there's a couple more patterns that are sometimes a little bit popular, but not as much. One of them is this. What if we have cubes? So the difference of cubes, right? We have a difference of, oops, cube there. We have a difference of squares. We also have one for the difference of cubes. And so this one I'll just give you, and also I don't expect you to memorize it. If I needed you to use this on a test, I would give you a big formula sheet and this would be on there. I think most people don't expect you to just have this in your back pocket, but it equals this. This is the pattern. So x squared, and then it's going to be plus xa plus a squared, and then also this. Now this does work. So subtraction of two things being squared does work. The subtraction of two cubes also works, but the addition of two squares does not work. It's not factorable, but the addition of two cubes is factorable. And this is going to be x plus a times x squared minus xa plus b, plus a squared. So this is it for the popular patterns. You wouldn't have any more to deal with. One thing to remember or to notice is that, see this pattern out here, x squared, 2xa, that looks a lot like this thing and this thing, right? Except it's missing the 2. It's missing a 2 there, therefore it doesn't factor anymore. So there's always a bit of a temptation to try and factor this even more after you've gotten to this step, but it doesn't. Okay, so let's look and see if we see some examples of these things. So as you're running through your list of things that need to get factored, let's look at, for example, how about something like this one? Factor r squared plus 20r plus 100. Is that something that fits this pattern? Does it fit the pattern or does it not fit the pattern? Does it fit the pattern? Okay, so what you got to ask yourself, okay, am I in one of these groups? Well, these are awesome because they're super easy to spot because there's only two things being either subtracted or added. So those are really easy to spot when you see them. These are a little harder, but let's go through them. If it's in fact one of these patterns, then it should be something squared. It is, the r squared. And then the last thing should be something squared. It is, that's 10 squared. And then the middle term should be twice the two things that you're squaring. Is that the case? It is, right? This is 10 times 2 is 20r. So it does fit the pattern. It fits this pattern right here. Right? It's something squared in the beginning, something squared in the end, and the middle is twice the two things that you're squaring, the x and the a. Twice the two things that you're squaring. And here I have something squared, and the middle is twice the two things that you're squaring. Okay? I didn't do any like math to it. I'm just recognizing that the pattern works, and now it's easy. All I know, now I know that this will factor as r plus 10 squared, right? Because it fits that pattern right there. By my patterns, I know that it works. Good?
Yeah.
All right, let's try another one. How about this one? How about factor 64r cubed minus 64, oh no, not r, x cubed plus 25. Okay, so that one is one of the easier ones to spot just because there's only two terms. Like, what else are you going to do with it, right? So the first thing you should do, though, is to first go through our list, right? Is there a common number or variable, a common factor to both terms? In this case, nope, there is not. Next is factor by grouping. Laughable, right? We need 4 terms, we only got 2, not going to work. Next, we go through our patterns, and it's got a chance of maybe being like this one, right? Maybe I can rewrite it like that. If I can do that, then that means that I can rewrite the 64 as something cubed. Yeah, that's 4, right? So this would be 4x cubed plus, and this is 5 cubed. So I can rewrite it as something cubed plus something cubed. It fits my pattern. Something cubed plus something cubed is this. It's going to be a little multiplication of 2 binomials, where the first one is these two things. So that's going to be 4x plus 5. And then this thing is going to be the first one squared. So that's this thing, 4x squared minus, and then it's going to be this times this. So it's going to be 4x times 5 plus that guy squared, which is 5 squared. Okay, so we can simplify this just a little bit and rewrite it as 4x plus 5 times 16x squared minus 20x plus 25. And there's that temptation to see if that thing will factor, but remember I said it's missing that 2. It's not going to factor. It has that temptation because this is something squared and this is something squared. Well, obviously we created it, but it's missing that 2. It's not twice the 2 things that you're squaring, so it's just not going to factor and you're done. Good? Okay, so this is the factor by patterns. We're down to 2 more left. Factor technique number 4, factor technique number 5. Okay, so the factor technique number 4 is this. Well, before I write it down, let me remind you of a little pattern that exists. Consider this. If we had something like x plus 3 times x plus, I don't know, how about 7? And I wanted to FOIL those things out. I get x squared plus 7x plus 3x plus 21, which is going to be equal to x squared plus 10x plus 21. Okay. Next one, how about x plus 3 times x minus 7? Well, that's going to be x squared minus 7x plus 3x minus 21, which is x squared minus 4x minus 21. Almost done. Oops, now how about if I put x minus 3, x plus 7, that's going to be x squared plus 7x minus 3x minus 21 equals to x squared plus 4x minus 21. Last one, x minus 3, x minus 7 equals to x squared minus 7x minus 3x plus 21 equals to x squared minus 10x plus 21. Okay, I did all these because I wanted to point out a little pattern that exists when you multiply 2 binomials that fit these particular patterns. So the first pattern we want to notice is that we are only dealing with one single happy little letter out here, an x. Could be any letter, but just one letter. And when you do that, one letter plus a blank, so a constant, times the same letter plus a constant, you're always going to get a 1 with that letter squared there. Okay? So, thinking in reverse, whenever we have something, a polynomial, where we start off with a variable squared with a nice 1 out in front, we should be thinking this is going to be the beginning of my answer, right? Just the letter by itself there, because that's how you're going to get the x squared. Okay, and now looking at the last number, that last number will come from the multiplication of these two numbers, right? We get 21 there, negative 21, positive 21. So that last constant comes from the multiplication of these. And the final middle term here comes from adding them together. So negative 3 minus 7 gives you negative 10. Negative 3 plus 7 gives you 4. And positive 3 minus 7 gives you negative 4. So it's just a matter of recognizing this little pattern exists whenever you have this situation. Only one kind of letter. We have the first term is that letter squared. There is a middle term that has that letter to the power of 1. And then there's a constant out here that doesn't have the letter. Then, if it exists, then the factorization will be a pattern that fits this, where these two numbers multiply to that one, add to this middle one, and then over here we just have that same letter. Okay, so let me write down what I need then. So, technique number 4, factor polynomials of the form x squared plus bx plus c, where the b and the c equal any numbers, any real numbers, except 0. Now, there's nothing wrong with 0, except just it makes the whole thing too easy. Like if I made b and c equal to 0, well then the answer is just x squared, so why are you bothering trying to factor? That's just x times x. Or if you made that one a 0, well, then the answer is also easy. They both have an x in common. Let's factor that out, and it just becomes easy. So we're just going to say except 0 just because otherwise it just makes the whole thing too easy. So examples are going to be things like x squared plus 7x plus 2, or x squared plus 14x plus 7, or right? Here's where the b is a 7 and the c is a 2, or the b is a 14 and the c is a 7, and so on and so forth. These are the ones we're dealing with. Okay, so my statement is this. If we have an x squared plus a bx plus c, also noticing that there's a nice positive 1 out in front, the answer, if it exists, not that it's guaranteed to exist, but if it exists, is going to fit this pattern. X plus blank times x plus blank. Now, I always put pluses here, but I'm open to the possibility that these might be negative numbers. Right? So I need 2 values there, 2 blanks. And I know that the pattern is that these 2 blanks multiply to this one, and I know that these 2 blanks add to that one. Right? Now, I don't want to keep saying the first blank one and the second blank one. So we think of letters for them. So we call them P and Q usually, or I do. So I want to find P and Q, the first blank and the second blank, such that the 2 conditions are satisfied. P times Q is equal to C, and at the same time, P plus Q adds up to B. When you find those 2 numbers, P and Q, if they exist, then that's your answer right there. You just fill in the blanks and you're done. Okay? So let's see if we can find one that fits that pattern, and then we'll be done with this one. Let's see. For example, let's run through the ones on here, see if anything pops out at me. How about x squared minus 11x plus 24? Done it? Oh, sorry, not plus 24, minus 24. Minus 24. Okay, so we want to go through our whole list of factoring techniques. Number 1, are there common factors? No. These 2 have common factors. That one doesn't have an x, though. And that's it. No common factors. That was number 1. Number 2, does it factor by grouping? Nope, because we need 4 terms. This only has 3. We're done. Let's not factor by grouping. Next one, is there a pattern? Does it fit one of our patterns? Well, this is something squared, but I can't write negative 24 as something squared. Done with that. Not going to work. Technique number 4 now. Does it fit this pattern? It does. There's a nice happy 1 right here, right? And the role of B is being played by a negative 11. The role of C is being played by a negative 24, right? So this fits the form x squared plus bx plus c, x squared plus bx plus c, where b is being equal to negative 11 and c is equal to negative 24. Okay, so I know that if the answer exists, and I'm not saying it will, but if it exists, it will fill out and give me this. The answer is going to be x plus blank times x plus blank if the answer is a nice pretty integer. Now the answer could be a fraction or an irrational number or an imaginary number, but we're not dealing with those right now. We're trying to find some nice pretty whole numbers that can fit this pattern at this point. Okay, so I don't want to refer to as blank number 1 and blank number 2, so I'm just going to call it P and Q. So I want to find P and Q, such that, P and Q, such that P times Q equals to negative 24, right? They multiply to negative 24, but at the same time they add to negative 11. P plus Q adds to negative 11. Can we think of those numbers? Do those numbers exist? They might not, right? So we got to think about our answers. How about 6 and 4? 6 times 4 multiplies to 24. No, I got to make one of them negative to make it negative, and then when I add them, negative 6 plus 4, that doesn't add negative 11. It's negative 2. Doesn't work. How about 8 and 3? 8 times 3, how about if we make the negative 3? That's going to be negative 24. But that's 8 plus negative 3. That's not going to work. That's a 5. That doesn't work. How about 12 and 2? 12 times 2, that's not going to work. That's going to be negative 24. But then 12 plus negative 2, that's 10. That's not going to work. And even if I flipped it around and made the other one negative, negative 12 times positive 2, that's negative 24. But that's negative 12 plus 2, that's negative 10. That's not going to work. Did we try everything? We tried the 6 and the 4, making this, making that. No, that's not going to work. How about the 3 and the 8, the 6 and the 4? Did we try them all? 24 and 1? That's not going to work. So if I tried them all, then I'm pretty happy that it doesn't exist. Then I know that there isn't any values p and q that factor that in a nice, pretty way. Got it? What could have worked? What would be so this one doesn't factor right now. Right? So this is, we call it a prime polynomial. This one is prime. No solution here. No integer solution, I should put. No integer solution. The solution is going to be either like a root number, like an imaginary number. It might be something hard, right? So we'll deal with that later. But for now, there's no integer solution. And so we say that x squared minus 11x minus 24 is prime. It doesn't factor anymore. Okay, but based on these things over here, I could figure out what I could have changed it to and gotten the correct answer, right? Or a factorable answer, right? So put it over here. What if the problem had been, say, factor x squared minus 5x minus 24? Can we see that in this case, the blanks are going to be what? I need two numbers that multiply to negative 24, but I need them to add to negative 5, so maybe the other way around. About a negative 8 and a plus 3. These two multiply to negative 24, but they add to the middle negative 5. We're done. That's how it factors. So if they exist, that's how it works. Good. It doesn't have to be that. How about another one? How about p squared? I don't know. It's about 7. Who's that guy going to be? Okay, so first of all, we recognize there's a nice happy 1 out here, and then there's a term that just has a p by itself there, and there's a term that doesn't have any numbers. Then I'm going to try this. Okay, and I want to fill in those blanks. Now I always write down pluses in here. That's just me. But I'm open to the possibility that these might be negatives, and then I would change it afterwards. So what am I looking for? For two numbers that
add up to negative 11, multiply to 30.
Okay. So what are they? What are any numbers that multiply to 30? How about 30 times 1? That works. How about 3 times 10? That works. Okay, but they're not going to add up to 11. That's not going to work. How about 5 times 6? Close. They add up to positive 11. We need it to be negative 11. Therefore, we make both of them negative, right? Negative, negative. So our answer is p minus 5 times p minus 6. This was the tricky part where you have to like kind of just think about different possibilities. So you have to be careful to write down all your possible solutions, possible combinations of two numbers and multiply to that constant. Because there might be a case like this one where there is no solution. And you're like, oh, you don't want to waste too much time thinking about them. So write them down. What multiplies to 30? 3 times 10, 6 times 5, 30 times 1. Don't forget the 30 times 1. The one that times 1 always eludes people. So there you go. Good? Good, good, good? Okay, and then finally we get to the last factoring technique, the AC method. So this method only works if you happen to have the very specific case of having a nice positive 1 out in front, x squared, some constant x, some constant out there. So it fits this form, x squared plus bx plus e. So the fifth factoring technique we're going to study in this class is factor polynomials. Factor polynomials of the form ax squared plus bx plus c. Okay, so this is where a is not 0. A is some number out there where a, b, and c equal any real numbers except 0. And again, that's just because it would just make it too easy. If they were all 0, the answer is 0 and doesn't factor. Okay, so there are many ways to do this. I'm going to recommend one way, which is the AC method. There are faster ways out there. A lot of people like the check and guess and check method, and that works great when these numbers are really easy. They're literally just guessing the possibilities and thinking about how to multiply them and figuring out which one's the one that works. And when these numbers are really small and easy, it's a great way to do it. But if they get a little trickier, then you could be there a long time guessing and checking the right answer. So the AC method, I prefer it for that reason. It's a nice systematic method to get to the answer. So this is one way of solving it, the AC method. I'm going to write down the instructions. They might not make too much sense right now, and then we'll see an example, follow the steps here, and we'll see what I mean. Okay, step 1, it is the AC method, so we're going to multiply a times c. Step 2, we're going to find two numbers, p and q, like we did before, except that we want the following, such that when you multiply p times q, it doesn't equal the last constant like it did before, it equals AC, the product of the first and the last. And also, when you add them, p plus q, it equals b, just like before. So that part's the same. This one, we're inserting the extra c in there. So you find those two numbers. Now, in the previous section, once you found the p and the q, you were done. You would just insert them into your answer over there, and you were done. So here, what we're going to do is once you find them, you're going to replace the b in your original polynomial. Replace the b with p plus q in the original polynomial. In the original polynomial. Okay, and then finally, step number 4 is going to be factor by grouping. Okay, all right, let's do an example. Let's see if we can find one. I'm just grabbing stuff at random here. Let's see, 8x squared plus 10x factor 8x squared plus 10x minus 3, I think. Factor that. 8x squared. Okay, so the first thing, we got to go through all our process, right? All 5 of them are built so that we catch the easy stuff early before we have to do the really big one. So is there a common monomial? Number 1, nope, nothing common to all 3 terms. Is it factor by grouping? Nope, nope. We need 4 terms for that. There's only 3 here. No. Is it one of our patterns? No, no, no. I cannot write this as something squared. I can't write that as something squared. Not going to work. Is it the fourth technique? Nope, because there's not a 1 there. I need a 1 to work. No, that's not going to work. We're left with the AC method. Got nothing else to do. All right, so we're going to recognize it fits that pattern. You don't have to write this down. I'm just pointing it out. So this fits the form of ax squared plus bx plus c, where the a is equal to an 8, the b is equal to a 10, and the c equals to -3. Okay, so let's follow the process. Step number 1, multiply a times c. That's going to be a times c, which is equal to 8 times -3, which is equal to -24. Step 2, find two numbers, if they exist, such that when you multiply them, they give you the result of step A, but when you add them, they give you the middle value B. Okay, so find two numbers, P and Q, such that P times Q equals to -24, but at the same time, P plus Q equals to +10. 10, 24, and 2. How about +12 times -2 multiplies to -24, but at the same time, 12 minus 2 or plus -2 equals to 10. I found them. Okay, now remember in the fourth factoring technique, once you found these, you were kind of done. You just fill in the blanks and you were done. But that's the case where there was a 1 there. So now we got to move on to step number 3. Replace the b with p plus q in the original polynomial. So back in the original polynomial, we had 8x squared plus 10x minus 3. We're going to replace this guy right here with this. 12 plus -2 is 10. So we're going to replace this with 8x squared plus 12x minus 2x minus 3. Okay, so what did we really do? We found a way to separate the middle term so that now we have 4 terms. Now that we have 4 terms, we're ready to do factor by grouping. So the AC method is really a way to force your polynomial to fit the 4th term, break up that middle term into 2. So you got 4 terms, now you can do factor by grouping. Okay, so factor by grouping, what is it? We focus on the first 2 terms. I like to underline it. Don't insert parentheses because you might mess up the signs. I like to underline it. Underline it. What do the first 2 terms have in common?
4 and
They got a 4, they got an x. Okay. The first term here is going to be 2x plus 3, right? Okay, so you factor that out, plus blank copy. Don't try and do the whole thing. People mess up the signs all the time. Right? Don't be a hero. Go step by step. Factor the first 2, 4x times 2x plus 3, plus blank copy, and now fill in the blank. And in this case, well, it's pretty easy. Blank times positive 2x equals negative 2x. Blank times positive 3 equals -3. So that blank has to be a -1. And now the final step is the tricky one, to recognize that they both have a factor of 2x plus 3 in common. Let's take that out. 2x plus 3, 4x minus 1, and we're done. All right, that's all 5. Everything we have to deal with in this book should be manageable by all 5 with only a few little minor tweaks here and there. And the only one I can think of that we do have to think about is this one. How do we factor this? So all 5 of these plus the following idea. There is a little trick that happens very, very rarely. So we only really run into this following thing. So factor minus 3 minus 28. A squared minus 3ab minus 28 b squared. Yeah, that guy. All right, how do we factor that? Well, notice that in everything I've been saying, we've always been dealing with one letter, one factor, right? And here we have 2. The only time you're going to run into more than one letter in our class is going to be either because the first factoring technique allowed you to factor it all out. In other words, they all had a common factor that simplified this greatly. Or in the little trick about we're going to be working with. So by the first factoring technique, nothing factors, right? They don't have anything in common. These two have an A, but that one doesn't have an A. These two have a B, but that one doesn't have a B. And there's no numbers common to any of them, so there's nothing you can do with the first factoring technique. So we're going to notice the following pattern. There is an A squared there. There is an A to the power of 1 there. There is no A. In the reverse direction, there's a B squared there. There's a B to the first power. There's a no B there. Okay. When you run into this pattern, and only when you run into this very specific pattern, this is what we're going to do. We're going to go off to the side, and we're going to solve this. We're going to put that one on hold. We're going to instead choose to solve this one. In other words, we're going to ignore the B for a second. Forget the B for a second. We're going to figure out how to factor that. Well, that falls under which technique? Number 4, right? It's not factored. They don't have any common terms. It's not number 1. It's not factored by grouping. There's only 3 terms. It's not one of our shortcuts because that can't be written as something squared. Okay, it might be the 4th technique because this is a 1. Meaning that this might be this. Blank A plus blank. That might work, right? If it does, I need 2 numbers that multiply to negative 28 but add to negative 3. Can I find those numbers? Negative 28 but add to negative 3. Well, what multiplies to negative 28?
Negative 7
Got it. Negative 7 and
and
4. They multiply to negative 28. They add to negative 3. We're done. Okay, so that solves that one, except, well, that wasn't the one we wanted. So just in cases like this, A squared A, no A, B squared B, no B, just in these cases, this is what we're going to do. We're going to write down our answer from that one. Who's this? A plus 4, like this. And then all we're going to do is insert a B right there. And it works. Okay? All right, that's it. That's all 5 factoring techniques plus this one little trick. We're ready to answer any question at all. Here is a random sampling of questions from the book. Is there anything from in here that looks scary and you want to attack? I think I'm going to stop this guy.